Hello, everyone. Thank you for joining today's tech section. Uh, all of our associates, all the scientists, all over the world, uh, whom I collaborate, they're not able to be present today, including Christopher, but they may join a little later, if possible. But I'm going to start the presentation of the history of physics, the seventh episode. So we have been going on with all the episodes, and then we are reached up to seventh. Now we are coming very close to the contemporary physics. We started from Galileo onwards, and then we noticed that one of the main thing is that we have the classical physics as high level of scalar aspects and the measurables that we use, the distance measurement or time or speed and even force and pressure and all that. We have all the gauges to measure them, and then but important aspect to note, especially from last week's leptogenesis update presentation by Christopher and the following discussion. We went through the idea, we went through a very important aspect that I am deriving from the time tensor aspects, which is a breakthrough, a new aspect in physics that people are not looked into earlier, but that I have published a few, and an ongoing analysis and the research projects um, going in full swing. In that one, I noticed that you can do a tensor degradation. That's one of the topics that's coming up, in one uh, a few journals that they have already peer reviewed. Um, and in that case, what happens is that you can degrade up to the rank one tensor, which is a vector. Realistically, we cannot go further than that, and there are some reasons we discussed last week. And that aspect is, later on, publication will show that it has to do with the referential aspects. Any potential, anything, there is not, we cannot measure absolute quantities. We know that even energy, everything, you need a reference point. And that's one of the main reasons. And then the reference point with the actual entity that we are measuring will have a vector. And this vector is very important because that, prevents us from scalar measurements. The how we get around in the classical physics is by defining the standards of these length, time, mass, and other aspects, even force and pressure and everything. So we have standards with which we are measuring, but of course the standards themselves can change, and we went to the problem ultraviolet catastrophe that required Planck to come up with the quantization of energy, and which has been proved. And then later on, the quantum mechanics developed. But unfortunately, general relativity and the quantum mechanics uh, went cross heads, and then have the vacuum catastrophe, the zero point energy, energy density, and so forth, are so much uh, meaninglessly higher orders of magnitude inconsistencies. So that resolution is finally now coming to quantum gravity, and that's what we started now last week. So today's presentation, I'm going to uh, I'm going to start presenting about the history of physics, ongoing things. Uh, so what we do is okay, essentially we are going to do a slideshow, a PowerPoint like usual, and then I'm going to start showing the history of physics. Okay. All right. So hopefully this will work. We always have certain issues with the uh, with our system, but that's usual. That you can expect that. my new system, so I had to adjust certain things. But I think we are okay. We are doing well so far. So I think I can start my presentation. So today's episode will be on history of physics. Seventh episode, physics now granulifying, essentially granulifying particle field theoretical modeling. So we came to the idea of eventually we are settling to from quantum and the relativity that everything is in terms of quanta and fields. Uh, that many other scientists pondered, like Sean Carroll and also Sabine Hossenfield. They have a lot of, and Susskind and from uh, Stanford and Lisa Randall from Harvard. They have all came up the idea of combining the quantum with the physics. And then, so my field, I work with both the quantum physicists as well as astrophysicists, quantum physics. When, Christopher is both quantum and astrophysics, and Emery Taylor, discontinuum physics. We are starting from a new understanding uh, that would, that would look upon the quantum and the astrophysics in a different light and see how they are. So then that is developing quite fast, and we have come up with a connection to find structure constant, things like that. So that's an exciting field that's going on. And then I work with Emmanuel Malaver, who is astrophysics, and we have analyzed all the Einstein things and then the new aspects of Bookdahl and other metrics, further from Schwarzschild metric to understand about the star systems and the black holes and magnetars, different astro objects as well. So and the measurements we have from many telescope, James Webb telescope and Einstein telescope, out to say Chandra, and different systems that look into the universe to understand the early part of the universe as well, how it all came into being. And there are questions about Big Bang and so on and so forth. But um, we have come up with certain aspects that even numerical relativity, things like that, has shown some idea of memory aspects that stays there. So present understanding is that that's going to present is that there is certain granular aspect of space-time, and also the fundamental aspect is superluminar, noisy, general condensate. My work with uh, right, Dr. Emmanuel Marco Lucas is the first one that started the publication of, you know, uh, two by two matrix of Helmholtz decomposition. Essentially, all the fields can be, classified into either, uh, as a transverse type of thing, which is, uh, in terms of string theory, it's open strings, but that also means that it's a 0 point field like cosmic microwave background radiation. So we can interconnect all these, and it's coming up to make sense. But there are a lot more research to be done. And also, the next one is the aspect that the longitudinal waves can become transverse with local locations because of distortion, creating distorted fields, and that eventually is the key to gravity. We are going to look into that much later after I finish our history of physics episodes and the documentary movie, which will show the gist to everyone, uh, scientists, and all the people concerned uh, all over the world. So the general public that can be used in schools and colleges as well. So general understanding is coming up. I think we are getting better understanding of that. Uh, so from that model that showed that you can have at the point level, we can have a 0 point or a micro black hole. Uh, so that's the idea. So like the longitudinal waves probably are, the noisy condensate, superluminal condensate. They are probably longitudinal and open strings. But local regions, because of the churning or the chaotic aspects of the superluminal thing, which is also called superfluids and things like that. Many scientists have come up with that, top Nobel laureates, that there has to be a superfluid type of thing that's covering the world, and that may be, the one that is visible is what we see, but one we cannot ever see with any type of experiments unless we have certain way of probing the dark matter or dark sector, which Emmanuel now works on the experimental side as well, of the dark photon, and he has publications on that level. Then I worked with also John Hodge. We have paper together on, and his scalar theory of everything is another big aspect that's part of that. Wen Zhang, he has published recently about how the Planck constant Hubble space will come together and define certain critical properties of the whole universe. In that respect, Christian also, the I space talks about how you cannot have anything zero level. Everything is a multiplicative aspect. And the I space essentially describes the granular nature of the uh, space time itself. And the GERD recently also published very important paper uh, uh, about how you can do uh, electrical circuits and circuit theory in order to analyze even up to the early universe, the Q factor and so on and so forth that he has come up with. And the phase angle. So the phase angle is important, as we have shown in one of the quantum physics, that the difference between the waveforms, original Maxwell electromagnetic waves are they can split into Zeeman splitting constant into electromagnetic fields, but the phase angle between them is critical. If the phase becomes zero, that becomes essentially, you can think as a photon. When it splits and then the phase angle develops between the electromagnetic fields, that eventually is connected with the fine structure constant, and the electric field then can become electrons and so forth. So their electric and magnetic, as we know from Maxwell equation, they're intertwined. And this aspect, has been proven. It's very clear from all the experiments, all the instruments that developed. That's the way it is, including radar and aspects. So it's very important to understand these classical notions, including Newton's gravity, which is termed into modified gravity. That in the previous episodes we went through them, and the quantum relativity. So the question how to bring them together is one of the key aspects. And as we know that from here, the YouTube, we have many videos uh, that you know that I have. Andrea Jimsa also had done earlier, but all of these appear in our YouTube videos. That's probably come closer to 100 or so videos uh, as we go along. Then we plan to have a world university, and in this auditorium discussion, philosophical holy grail of physics conservation. Again, I'm coming up with the idea of time conservation, things like that, that publications will come up a little later. Uh, but we'll have the auditorium where we just talk about it and then come to the same, we all come to the same understanding and same page, so to say. And then we will have an informal presentation. And many of these episodes will be highlighted there. All right. So the historical perspective is the key thing here, because I think that shows the non-speculative, objective way of looking at the physics itself, how it developed over a period of time. And then, as we know, Professor Hawking's brief history of time is a very good example of the importance that we have to pay and understand, straighten our minds with respect to the history itself, because the time is moving in that direction. And one of the things that came up is because of the gravity, the time is going forward, the arrow of time. That's one aspect that's coming up from the vector aspects. But those are all ongoing research now. But essentially, we have the quantum gravity. That is the most, uh, you know, theoretical aspect that most scientists are kind of agreeing on that we need that. Uh, there are pluses and minuses about that. So we'll go through that today also. Quantum gravity and effective field theories. The search for a theory of quantum gravity has significantly influenced our outlook on fundamental physics because the gravity right now is a local phenomenon, as we know, but the electromagnetism is a global phenomena, and how they, how they interact together, how they come together is a big question. That is, both theoretical and experimental physics is probing into. So EFT, which is the effective field theory, treat the standard model as an effective field theory. The standard model is based on the fact that everything is fields, and then from there the quanta is formed, things like that, played a pivotal role in the transformation. EFT views the standard model as approximation valid up to certain energy let's scale. So these are okay. Even LSC that measures the trying to prove about the standard, which has proved our standard model, especially the weak theories. It depends on the energy levels, how much we can get. Is because of the particle collision, especially proton-proton collision, hadron collision, that brings out all the particles, and the energy levels they can reach about certain tera electron volts, things like that. But they are trying to see more and more particles. One of them being the Higgs boson that they saw is what excited people to go further, beyond which new physics, quantum gravity emerges. So definitely, we have to understand the quantum aspects, the gravity aspects become important, especially in black holes, and I think that everything, because of two aspects only remain, 0 point and the micro black hole. That is something that's coming up, but I don't want to, uh, expand on that because we are looking to the history aspect and coming closer to these 1930s or the 20th century. From the 16th and 17th centuries, we are coming to 20th century. So in the 1930s, physics attempted to quantize Einstein theory of gravity. So that was Einstein theory, of course, was the most fundamental that has been proven with a lot of observations that his mathematical derivation, general relativity, is the keystone in many other physics and ongoing still. But there are a lot of questions that has opened up, especially how do you explain the gravity, particularly using quantum field theory. So that's where quantum field theory comes into picture. The early effects laid the groundwork for understanding the play between quantum mechanics and gravity. Okay, so 1994, Steven Weinberg, another great scientist who's alive till recently, marked the beginning of, who has done a lot of work uh, towards the Nobel Prize aspects, things like that, to mark the beginning of modern bottom-up approach to general relativity. So he said that we start from the quantum aspects and then go up to general relativity, and then so that we can develop the effective field theory. The string theory is a top-down approach. The string theory looks at from the opposite point of view. Uh, that emerged in 1980s potential framework for quantum gravity. So, it's simplified in terms of instead of particles, the smallest entities are considered to be strings. Like I said, the open strings and the closed strings or loops. So it provided top-down perspective aiming to unify all forces, including gravity. So, typically it talks about the time, electromagnetism, things like that, and how the vibrations of the string is fundamental. So meanwhile, EFT continued to drive the bottom-up perspective. So hopefully this bottom-up and the top-down will meet together and then find some kind of a resolution, correspondence that will help to unify that. So in the 1990s, that happened. So the current press work is it's all ongoing is the swarmland included the swarmland conjectures, especially the which said that there are no global symmetries, essentially saying that the gravity is highly localized phenomena, and then we should not be looking at the global aspect or global symmetry. As we know, Noether's theorem is uh, the most fundamental aspects in the physics. We actually everything resets to Noether's theorem of symmetry. So that's very important. But the Swampland conjecture said there are no global symmetries. Concepts like moduli stabilization and Swampland could guide their investigation. So there are many aspects, concepts, and theories that came up based on that. Compared with quantum gravity and string theory, no global symmetry, says Pointer, either broken or gauged. So the gauge theory is another important aspect that we'll start touching upon a little more. And I already talked about a little earlier episodes. Uh, for instance, Hawking radiation only detects charges measurable outside black holes, which are gauge charges. So uh, the gauge essentially means that, as we know, in general, if you want to loosely understand about the gauge aspect, is because we add any constant, and when you find a differential, the constant disappears. So that's the idea of the absolute aspects that we actually perturb in a constant manner or transform. Then we find the differential. The constant drops out, so that we get uh, essentially a gauge, or we can get a symmetry invariance. So we get a invariance that depend transformation that helps to understand measuring one aspect, we can get understand about the other aspect. So that's a gauge theory uses that, and also multiplicative aspect. If we multiply by constant aspect again by unitarization process, not renormalization, things like that, we can actually come up with a proper correspondence. So the gauge theory has become the key aspect in understanding these things. Okay, let me put that. Something happened to the presentation, so I have to again put it back. Um, okay, so let's move on. Um, okay, so the concepts like these are coming up, especially gauge aspects and Hawking radiation. Uh, so that the anti-de Sitter and the conformal field theories, or generally called as CFT, correspondence also support the conjecture of the anti-de Sitter space. So these are all additional things that anti-de Sitter is inside something, and de Sitter will be outside something in a general sense. So we are looking from inside. So yeah, the anti-de Sitter is quite important, and then how that converts to conformal theory that is outside. So from inside, how do you understand outside? It is very important to understand about the universe itself, the local level with the quantum aspect, and the global aspects, which is the astro aspects. So modern global and gauge theories allow for a natural extension to higher form symmetry. So we know more and more higher symmetries exist, and uh, and that's what driving the whole universe in many different directions. That will impose restriction on scalar fields and potential, but also the scalar fields are restricted by these symmetries. Okay, so what is happening is that eventually all this come together and coalesced into the understanding of special unitary general group. So the group theory has become important because the symmetries are the key to understanding the properties of existence itself. So SUN group in quantum mechanics, a special unitary group denote SUN is a Lie group. So what is a Lie algebra matrices look like this? SU2 matrices which has quaternions in them, right? And They have U1, U2 uh, submatrices which look like polymatrices, and they have quaternion relationships. Using that, and then we use committed bracket. We can actually describe SU to a eight-dimensional symbol consisting of only 3 by 3 matrices with determinant one. So the uh, the aspect that we have to consider is the very fact that excuse me, very fact that there is a unitary group of one in this matrix. So 3 by 3 will have 9 elements, but one of them is just a unitary value, so that you only have 8 real variables elements. So spin rotation operator. So you can use spins, as we know, particle. The spin is very important. So we have the spin aspects coming into picture. Uh, so this light group describe the symmetry. So they have observation by protons and neutrons. The scientists have developed that coalesced understanding that despite the charge differences, they have similar nuclear behaviors. It's called isospin symmetry. So the isospin tree is one of the things that help to understand uh, the different types of SUN group, the SU3, SU2, SU1. So the concept of isospin, isobaric spin or isotopic spin led to the development of quark model. So this came to an understanding of the SU3 group, key to the Gell-Mann matrix that developed for the strong nuclear aspects. So this is octet structure uh, that was developed from the Buddhism principles, connected to Buddhism principle as well. But they have all these, specific symmetry groups. So this Koch model proposed by Gell-Mann and George Swig, uh, discovered 1950s and 60s, explained complex spectrum of stable hadrons. Hadrons are like protons, neutrons, and the big particles that originally Rutherford identified. Rutherford, other Thomson, other initials. Uh, I would call them particle physics to start with. Started understanding the nuclear aspects. The strong interaction with the mesons, the middle class and baryons and heavyweight. So the mesons are the middle masses, whereas baryons are the heavyweight entities. The hadrons led to the concept of flavor SU3. So I generally will call it entity because they may have spin but no charge, and they may have spin half or one, but they may not have mass, may not have charge but mass, like neutrons, for example. Uh, and you have photons, or they are bosons, but they may be massless. There are photons that will come into uh, detailed discussion of the four forces, which are which is which we are trying to try and unify. We start with electromagnetism, gravity, strong nuclear, and the weak nuclear. So we will be going to each aspect because the details of that are highly mathematical as well. And that's one thing we have to really decode. So the hadron led to the concept of flavor SU3. This eightfold way organizes, this eightfold way is the original Buddhist principle, but it helped to organize the eight spin zero mesons into an octet. So that's an octet. Having kaons, these are the kaons, uh, these are the kaons. Then you have pions, you can call them, and eta, the diametrically opposite particle of octet. So Uh, so they form antiparticle, but they also say that they should be antiparticles for the case of symmetry. If you are charge 0 q1, then there should be a charge -1. Of course, for the electrons are charged -1, so they should be anti-electron, which is positron, that is charge 1, things like that. And the octet antiparticles are interconnected to keep the symmetry and the minimization of energy, things like that, that even Feynman had pointed out, corner field theories. They issue three hadrons based on their chord content successfully predicted properties. So many other properties could be predicted based on this quark model. Um, and so then people started excited, started to have excited feeling that we probably could come up with a theory of everything using supersymmetry group. But the supersymmetry group, which is also called SUSY, uh, proposes symmetry between particles with different spin properties. So quantum mechanics identified spins, right? You have fermions, like electrons have half spin. Bosons, like the photons, have a complete spin of one. And then you have gravitons. It's a theoretical thing. It has not been proved, but possibly have, spin too, depending on the rotational invariance aspect. Uh, our 4D space, we may have to consider 4D space. The quaternions are involved in that. All right. Example, every non-particle like fermion, there exists a partner particle like boson with similar mass, so but different spin. Okay, pointed out. SUSY fermions or electrons are super partners called sparticles, which are selectrons, you can say, or s electrons, and vice versa. So this is the supersymmetry because there is something symmetrically, opposite. For a chiral symmetry is different, but that also comes into picture later on. The SUSY remains experimentally uncounted, but it could prove this aspect of having super partners. Even, but theoretically, a lot of implications in particle cosmology. So the application has been seen. Supersymmetry, excuse me, could help explain phenomena like dark matter. So right now, the astrophysics came of the understanding of dark matter to take care of the energetics of the universe and the gravitational effects, how they interact. Uh, so the dark matter is constituting the universe's most mass, and the hierarchy problem that SUSY reasons relatively like that by stabilizing his. So Higgs boson mass is important, and and then how that get lightened by the Higgs boson mass, uh, because dark matter is supposed to be a very heavy particle, a weakly interactive massive particle. WIMP is supposed to be one of the particles associated with dark matter. It's all theoretical, present, doesn't mean no proof. So the SUSY has rationale based on for that. Excuse me. So having extensive searches, no direct evidence for SUSY has been found yet. So heavy particles such as the neutralino, which could serve as a weakly interactive massive or WIMP extends standard model. Excuse me. So, so the standard model, we have to go further than the standard model. So theory for everything is such an attempt to unify fundamental forces, gravity, electromagnetic, strong, and weak, single framework. String theory, which incorporates QC, is a candidate for TOE or theory of everything, capable of providing complete description of universe at all scales. QC's potential predictive power. Set of superpartners corresponding to non-particles like selectrons, uh, which has superpartners, electrons, and gluinos, the superpartners of gluons. As we know, gluons are the key particles that holds the strong uh, field together. Neutronions, which are potential dark matter candidates. So all these are very important, inferences from the SUSI. Particles uh, are heavier than standard model counterparts. When particles decay, they often produce invisible particles that escape detectors. So the present type of detectors are not able to sense these. Detecting missing energy signature key strategy in collider experiments. So by looking for the missing energy, even including eventually micro black holes or black holes, so to say, probably they exist hidden in these aspects within the dark matter. Uh, that's something continuous probe, but they need a much higher energies, which at present is not achievable yet, but they're pushing the limits. And let's see. Excesses in specific channels, jets and missing energy may indicate particle protection. However, high energy equipments may be beyond current collider energies, apart from problem of and also depends on model having different SUSI synodies leading to distinct collider signatures. So looking for signatures that will indicate that indeed the supersymmetry exists. So that's a highly challenging aspect still. The quantum fields and the standard physics model relativity and the relativity together. Uh, Quantum field theory combines classical field theory, quantum mechanics, and special relativity. Particles are known as quanta, excited, excited states, and underlying quantum fields that holds them up. So they form the matrix that holds this quanta, which are more fundamental than the particles themselves. So the fields are the fundamental aspect from which the quanta is formed. QFT or quantum field theory models as uh, subatomic particle physics and quasi particles. So they're the quasi particles. They may be the intermediate between the particle and the field, uh, and they are form part of the condensed matter physics. The standard model is based on the QFT or the quantum field theory. Fundamental particle interactions. The key thing is developed by Feynman and other scientists is they are mediated by exchange particles or gauge bosons associate various forces, electromagnetic, weak and strong. So there is a mediator that helps, like photon is one of the mediators for the electron and the positrons to become quarks, right, and gluons and things like that. So the Higgs boson is a very specific particles that is the key to creating mass uh, from the Higgs mechanism, who got all the prize as well. Uh, so that's one of the exciting aspects that collider experiments had been able to come up, have been able to do years ago. So special relativity is a fundamental theory that describes behavior objects moving at high speeds, like we know, close to the speed of light, applying Lorentz transformation, time dilation, and contraction. So again, these are questionable, but right now that's the most accepted theory. But when combined with quantum mechanics, they may come up with a new theory that will use all these concepts, but in a modified fashion, even including Newton theory. The QFT and special relativity possible combinations ensure consistency across different reference frames. So Higgs mechanism or okay, Higgs field and symmetry breaking and beyond standard model. So that's a very important aspect of symmetry breaking aspects. So Higgs mechanics explains how the W plus minus and the Z weak gauge bosons, weak nuclear interactions acquire mass. We know that the Salam model that we'll touch upon a little later talks about and has been most successful and becomes the key part of the standard model. And the Higgs aspect essentially proves that the standard model aspects. Higgs field permeates all of space and causes spontaneous symmetry breaking. So the symmetry means that remains dark matter, positive and negative together. But the symmetry breaking means you have matter over antimatter. or particles over antiparticles. That's the symmetry aspect, so that we get the baryonic universe. Um, so symmetry during particle interactions, these are spontaneous reactions, like we see in chemistry, spontaneity of the negative free energy, the Helmholtz, and the Gibbs Helmholtz aspect of the energy in the form thermodynamics. So thermodynamics is becoming very important in these physics, in quantum gravity, and further theory of everything that we'll examine later on. The breaking of the symmetry triggers Higgs mechanism that will grant mass to bosons interact with. So bosons are supposedly massless, like a photons, but this Higgs mechanism gives the mass. So in 2013, about 10 years ago, Large Hadron Collider, let's see at CERN, confirmed existence of Higgs boson, for which Peter Higgs and Engler, Francois Engler, were awarded Nobel Prize in Physics. Higgs mechanism is cornerstone of standard model. Other theories, supersymmetry, propose additional types of Higgs bosons need to be understand more. All right. So going beyond standard. So now we have very good, at least qualitative understanding. And the quantitative aspects are highly complex, like I say, mathematically intrusive, that the history of physics doesn't enter into that, has to be a proper in different part. And we have courses and books and videos and, and then papers that, articles that, go into detail, the mathematical detail of all these things and highly complex phenomena. So quantum gravity and unification. Gravity. The most significant gap in standard model is absence of consistent theory of quantum gravity. Incorporating gravity into particle physics remains a formidable challenge. Cosmology, dark matter and dark energy are mysterious components of the understanding their nature is very crucial to understanding everything about the universe, how we came into existence in the first place, things like that. Matter and antimatter asymmetry. Why does the universe predominantly consist of matter rather than antimatter? So that's a big question mark still standing. Uh, we have no real answers for them yet. Arbitrary parameters. Standard model contains numerous parameters, the mass of the electrons that lack deeper explanation. So you have to go into more detail how the mass came to be, so on and so forth. Planck limit set by the Planck limit is supposed to be the limit between the field and a particle itself. The standard model is a low energy approximation. At energy approaching Planck scale, we are talking 10 to the power 19 GeV, giga electron volts. Gravity becomes significant. So the model breaks down. So the current model, standard model, is not able to explain that. More fundamental theory, like a grand unified theory, could unite a strong, weak, as well as, sorry, global. Oh, this has to be okay. Local and global magnetic forces, or weak should be a spelling. Okay, I have to correct that spelling. Uh, Okay. String theory and ultimate unification attempts. String theory proposes that fundamental particles are not point-like, but tiny vibrating strings. So, possibly, like I mentioned before, possibly unifying gravity to other forces could potentially serve as candidate theory of everything. String theory remains theoretical and awaits speculation. There is no experimental validation to prove any aspect that of the thing, even the vibrating strings, things like that, has not been able to be proved by any experimental method so far. So gauge symmetry and group theory. Uh, gauge theory, a field theory, there's a Lagrangian mathematical system dynamics unchanged by certain Doppler transformation is one of the key aspects. Lagrangian talks about the energy, right? The energy difference, the kinetic energy and the potential energy that's driving the dynamics. So Lagrangian is the most fundamental aspect that um, gives the final, so to say, of the action itself, which is Lagrangian over integrated over time. very similar to Planck equation of energy integrated over time is a constant, right? That's conservation aspects as well, and the quantum, but it's a quantum conservation. It's very important to understand. This transformation, gauge transformation form like group. Uh, symmetry group or gauge group that creates kind of invariance that we can use those properties. Gauge refers to mathematical formalism used to regulate redundant degrees of freedom. So in the Lagrange, there are a lot of redundancy, and that's removed by the gauge. Differentiates it out, you can kind of say. Symmetry and gauge invariance. The gauge theory is important because they successfully explain dynamics of elementary particles. So they even go all the way to Maxwell equations, and you can use gauge theory to connect all element in terms of potential, and you have four vector potential, things like that. That become very important. Gauge invariance ensures the Lagrangian is unchanged local transformation. That's the key thing. So the Lagrangian will change unchanged, and we can utilize that aspect to understand something that we don't know. Much like in algebra, something unknown, we can figure out by using this. Uh, Once we prove up the gauge invariance. When quanta is the quanta, the gauge fields are called gauge bosons. So they are gauge bosons, which means they can remain invariant under these transformations. And like we say, no, like a catalysis that we use in chemistry or physical chemistry, these bosons participate and drive the interactions, but they don't themselves get transformed. So so this is the idea uh, of the invariant aspects. The examples include quantum electrodynamics, which is one of the advanced ones in the 90s, further down, 80s, 90s. Abelian gauge theory with the symmetry group U1. So U1 describes the electromagnetic photon as a gauge boson. So the photon aspect is the U1, that is element one, uh, the photonic vector, so to say. Standard model. Standard model is a non-abelian gauge theory. So, then we need higher matrices in terms of U1, SU2, and SU3, and that totally involves 12 gauge bosons. Uh, the photon, the like we mentioned here, the three weak bosons and eight gluons. So, for example, SU2, like I mentioned, uh, is a 2 by 2 matrix elements, but one is unitary. Therefore, we say that it has only three weak bosons, right? The other one is just a unitary aspect that because of the determinant of the Lie group is no, Lie group matrix will be one. So these are mathematical adjustments that creates the understanding of the existence particles themselves. General relativity and gauge gravitation. Even gravitation is described a gauge theory. So the understanding that we can extend this field theory, field gauge fields to gravity itself. So in general relativity, the gauge field is at so the general relativity is converted, processed by the gauge theory. Um, then we can say, uh, you know, uh, the gauge field itself can be described as a Lanzone tensor. Okay, so certain aspect of the Einstein tensor, the Einstein general relativity, is the Lanzone tensor in the gauge theory. So rank three, that's a rank three tensor in general relativity that generates Weyl tensor, measure of the curvature of space-time. Okay, you have Ricci tensor, things like that, that describes the curvature, but they are pseudo-Riemannian manifold, which is not degenerate because they're not, uh, they have unique uh, aspects that comes from there. properties. So they don't uh, fall back into something of a trivial aspects. So it's non-trivial. That's the key thing in all the theories. And gauge theory removes these trivial aspects and keeps we get a non-trivial solutions of the field itself eventually. The theories of quantum gravity, like gauge gravitation theory, propose external gauge boson called a graviton. So that's how the understanding graviton, which seems to be the most fundamental particle, and Emmanuel talks about that, about the graviton itself, is the most from which you can actually form the the bosons and the fermions. Uh, so yeah, analogy to gauge covariance. The covariant vector is very important, as we know, in general relativity. That is migrating into the quantum mechanics also. Gauge symmetries are analogous principle of gauge in covariance in general relativity. Okay, both reflect densities in the system's description, allowing coordinate systems to be chosen freely. Okay, um, so that's one of the aspects. So gauge theories play a fundamental role to understand the behavior of particles and forces, bridging the classical and quantum. So we think that higher theory, when you use some specific limitation, then it becomes the quantum mechanics and general relativity and then finally the classical theory, right? So the constraint how we impose on them will determine the differences. Okay. Finally, we come to the understanding, which we'll be talking more in further episodes than theory, which is brains and everything, and the superstrings and the brain modeling, what these are. We'll start understanding a little bit in this episode, but we'll go into more detail because that's the upcoming emergent theory that can explain most of those phenomena from quantum to astrophysics. So M theory is a fundamental theoretical framework that aims to unify all consistent versions of superstring theory. So it does use the superstring theory, as we know, and it was proposed by Edward Witten. The M theory emerges umbrella theory encompassing the five distinct superstring theory. So the string theory itself has many different connotations and aspects. These things seemingly different are intricately related to mathematical dualities. They are called as duality, T duality. I'm not going to go into mathematical research. We know I'll refer to the standard. I'll be giving a lot of references at the end that talks about these. Uh, while a complete formulation M theory remains elusive, it should involve 11-dimensional objects called brains. So the brains are 11-dimensional objects. Okay. The approximate 11-dimensional supergravity law energies. So these vibrations are different dimensions are the key to the string theory and eventually the five distinct superstring theories. Superstrings and brains. Superstrings are fundamental objects in M theory. You can kind of think that how uh, the needle and you know the strings how they become cloth, making cloth or fabrics, right? Very similar. So it's highly complex thing aspects. So the M theory is trying to understand that the vibration at higher dimension, giving rise to particles. So the particles are eventually formed from this vibration of the strings at higher dimensions. That's understood. Brains are extant objects, higher dimensional analogs of strings that play a crucial role in M theory, right? So they stick together, vibration and consistently, somehow come together and eventually form the So D brains, which carry open strings, as I said, mainly the concept of string theory can be boiled down to open strings and closed strings. The closed strings are the so D brains carry the open strings, and then two brains are the two-dimensional brains. The brains provide a geometric framework for understanding gravity and other aspects. So the geometric aspects is you know perused and rigorously used to in the brain, young brain theory, you can say, uh, and that will give the understanding of gravity, which is a local phenomena, uh, and other forces which are global phenomena. Cosmological implications. So, how does the global thing become local? How does the local thing become global? It's a fundamental question that we are to hopefully able to answer as we go on the developments of the theories. Cosmological implication. Brain worlds in origin proposed observable universe exists on a brain embedded in a higher dimensional space. So there's higher dimensional space, can call matrix, whatever you want to call that for now. Uh, and the brains are embedded in that. This model offers alternatives cosmic inflation and address questions about the early universe. So that's one of the theories about the Hubble tension and the cosmic inflation and the expansion of the universe. And many scientists think that it's expanding much faster rate than we ever thought. Okay, so in summary, M theory unifies superstrings, brains, and gravity, inspiring both theoretical investigation and potential connection to experimental. So that's the idea we'll touch upon. We come across, further episodes. We'll be expanding on these aspects. So thank you very much, and then uh, you have the YouTube live broadcast available that I have mentioned earlier. With the link. So the upcoming episodes, episode 8 to 10, will continue analyzing gravity, space-time, quantum, non-locality. Again, like I mentioned, previous episodes also, and then the further episodes also talked about, uh, especially the Bell's theorem, things like that, about the locality and non-locality uh, in astrophysics. Altropic unification, and that's the most fundamental thing that proved the standard model. Quantum chromodynamics that the normal audience will set everybody as advanced, and that can explain again a unifying aspect. Uh, that's developing. We'll go into detail about that. Loop quantum gravity, which is upcoming, again that talks about the granular aspect space time. We'll talk about M theory that I briefly described. I started introducing the brains and the gauge theory, modifying classical emergent fields, and the combinatorial matrix theory of everything and unified models. Okay, so these are the references. Uh, Many references occur. Swampland conjecture I talked about, no global symmetry, quantum theory, introduction to unitary symmetry, very important part. SUN groups, the unitary symmetry, strong interaction, and all the different types of interaction, and the flavor symmetry, quark model, isospin symmetry. Again, the references for that and the groups. Also, there is a group called GU and then SU, PGU, different groups. How they interconnected. There are kind of maximum subgroups, ordinary characters. They're trying to classify into categories itself. All right. So QCD, the quantum chromodynamics, then Lie algebra. Again, these are the references that you can look into more. They're highly mathematical. I should emphasize that they are highly mathematical because by high level knowledge of the math. Uh, but that's become part of the physics now. But we should, and I feel that we should apply applied math so that it becomes easier, and also coding things like that we are trying to do, Christopher. That will help in understanding the physics itself. What is supersymmetry? The standard model, generation of particles, gauge bosons, Higgs mechanism, and beyond standard model. Because standard model still is an incomplete theory, because for the reasons I talked about in this episode. And then we have the new physics beyond the standard model. What lies beyond the standard model? gauge theory, right? And the gauge theory and the standard model, how they are coming together. Then we have introduction to Yang mills. Again, the Yang mill problem, that is the mass gap, things like that is very, very important. The weak and electromagnetic interactions, how they were able to combine them together. Introduction to Yang mill quantum theory and generalized Yang mill theory. Introduction to spontaneous pre-breaking. Like I mentioned, the Higgs boson, the Higgs mechanism. The loop quantum gravity, right? I started developing that. We'll look into more into that. Foundation space and time, reflection, quantum gravity. Then brain wheel theory, how the brains, the 11 dimensional aspect of the superstring theory come into picture. And they explain the gravity aspects. The three algebra and gauge theories, specific aspect of gauge theories. And then Kaku himself is that the M theory and the mother is the mother of all superstrings. And that is described in this particular uh, small presentation that you can look into that in more detail, and uh, and then we can understand the physics behind the simpler aspect as well. So that essentially should cover episode 7, uh, and that launches a stage for episode 8, which will be done next month. So we hope that you know we have better understanding of this complex phenomenon. It's very confusing, right? Sometimes very confusing, and that using the history we can straighten our minds and then get wrap our minds around the real things, how they develop, how they help to uh, develop uh, the you know the theory is very important to understand. But of course, it has to be validated by the experimental techniques. One of the problems think theory has, but my understanding also is that we can develop the theory to the level that we come up with some predictors and project certain things that can be checked later on, and then that will serve as a proof of the theory itself. So we can work together on that, and that will help. And that's the idea. History of physics looks at more quantitative, more easier way of looking at the physics itself without the confusion of math. Sometimes the math can be very confusing and very difficult to understand, and then we get lost in them, and we think it's the math that guides the thing, whereas the physics itself is the most important aspect from the standpoint of understanding of the actual properties. The math is a tool that's very helpful, but it stops at a certain level, right? And then I'm going into more detail about those aspects. I'm developing also the math, and I want to point out a couple of things. I want to apologize. I want to excuse the fact that I had to make some correction in describing the last episode. I did, make. So let me pull out that. Hopefully, I'll show you that where I made a mistake, a simple mistakes, and as you described, but something I had to correct. That I said that 100 grams is 0.01 kilogram. Really, it is 100 grams is zero point 0.1 kilogram, right? For example, in the lab episode discussion with Christopher. Uh, so let me try to pull out these aspects. Uh, okay. So they come in the discussion somewhere. So I'll just briefly go through them and point out certain things that you can see, and some corrections had to be done or corrigendum type of thing, and that's what I'm trying to do. So I started with these a few episodes ago, and you know Yeah, I want to ensure that you can see it as well. Um, okay. So these are previous episodes I talked about the signal being the ultimate observation, right? And then we have a code axis, much like the order in physical chemistry of reactions, multi-step processes. In chemical reactions, it's called the order, and that's plotted against a coordinate axis, and we don't know that coordinate. So we describe that signal at the coordinate axis, and we know that at present what we know, and then later on we can change. But that's the most general aspect. But these chord axes are going to become the space and the time. The space itself is described by higher dimensions, so x to the power n, where n is like the rank of the tensor that describes the space, which eventually becomes a dimension of the space. So it makes more sense for space. And there are questions as to why the space is three-dimensional, higher dimension space. Higher dimension space is Cartesian. Then we think that it is. Sometimes people think that the space actually is a fractal aspect, which is not completely 3D. Hausdorff dimension, which is like fractional, your fractional dimensions between 0 and 1, 1 and 2, and then 2 and 3, especially like snowflakes and things like that, which has certain 2 point something between 2 and 3. So they actually describe the fractal aspects, but that's something that has not been understood much in the physics, and probably will come up later on. But for now, and then time, my publication showed that it's a tensor. Again, it's a rank 6 tensor. So again, t to the power m, right? And so I'm going to publish that. This I'm just going through that. Don't worry. If you don't understand something, I'm not presented in deep, but I'm just giving you glimpses of that. That's all. All right. So the signal spectra, we have to take it's like gauge theory. You have to gauge it, or we can use the tangent space to describe because that describes the motion. The tangent space is very important in physics, and that differentiate differentiated signal with respect to we once we know that what the chord axis is, like a space, and then we have time, we can differentiate with respect to and see the changes because what we can measure is are the changes. All right, so x to the power m, when you differentiate, we get power density, things like that. So we're going to map later on, and our publication will show how that happens, and then we can talk about that aspect. All right. So some other corrections, as we know that, that's why I'm going through it again. There are some things that I corrected here on the previous ones. The Fourier analysis. So we have a uniform, like a sinusoidal or Sita-Bowang, uh, you know, uh, oscillations. But then we have high level modulated thing, which probably like gravitation waves create that um, high peaks. Um, Even Dirac type of delta function that can go into infinity. But you have the normalization thing. So these plot will help to figure out the signal to noise. So that's one other normalization aspect, the signal to noise ratio. If we talk about a signal that becomes infinite, we have to renormalize, and the signal to noise ratio helps to normalize that, renormalize in some respect, and become closer to the gauge theory. So we have two different types of fields, and when I look into those fields, interesting things happen that I talked about a couple of episodes ago. about the continuum aspect and also how these fields add together. We can add these fields together. These are different fields. And when you do the mathematical operations, we see that ends of the world or the nodes can be vacuum on one end because we can convert this signal into a temperature using Boltzmannian, Planck-Boltzmannian type of generalization. Using that, we can show that the ends of the world, one side is the vacuum, the other side is the superconductivity. So that's a very interesting aspect. So we have vacuum solutions and the superconductive, especially at the absolute temperature, it becomes superconductive. And then at the very highest energies, they become vacuum because they pull out everything. They become ionic, plasma, and even further than that, it becomes even rarefied and becomes the vacuum. But vacuum is not empty, as we know that. So this will support that, why that comes in the picture. Anyway, I'm just giving glimpses, and we'll talk about these in our documentary movies, some of them I'm talking about. It's a little more interesting aspect. But we can classify everything in terms of categories as the whole universe in terms of matrix, entity, vacuum, and quanta. So the matrix and the entity exist in the matrix. Like I said, the brain theories support this aspect. And specific aspects of the vacuum evolved. So the vacuum is a dynamical evolution, it's not statical, where it keeps the speed of light constant. Then the quanta has all these mixed aspects, right? Um, so that's how the real world and ourselves come to the particles and ourselves come into existence. Then I talked last week about the interesting aspect I found about the charge and the mass. The charge and the mass are based on that versus the spin. So we can talk about the spin spectroscopy type of thing. That's our additional spectroscopy. Energy spectroscopy is what we use in LHC, but you can use spin spectroscopy, and interesting things happen. The fermions, especially the electrons, it can exist in different states. Electron, muon, and tau, which is higher masses. So and when you plot the E over M, which is the fundamental aspect of classical theory, most important aspects, the property aspects. Then for bosons, they have a spin of one and indeterminate because the charge and the mass are going to zero or it becomes chargeless, you can say, and the massless type of thing. So they are very botched areas, indeterminate areas. But within that exist, we can show later on, and I'll prove out that within that exist the cork model. Within that exists. So within this messy, smoky region exists a very clear, like I call it the uh, candle in a cave. That's it. So the cave or cloudy thing within that nebulae, Orion, how the Charlie Polycan micro black holes can develop. Okay, so that's interesting aspects. So then the gravitons, which are theoretical particles, that's mass of two. Again, they're supposed to be chargeless and massless. Uh, that I discussed with Christopher last week. All right. So, and other interesting aspect that I'm talking about with the Emery is that the phase angle we find in the sinusoidal wave to describe the discontinuum lengths or discontinuum aspects is indirectly related to the fine structure called alpha. And I have actually developed that, and we have actually come up with a program that is proved, and then the output show very clearly the direct relationships, and then that publication will come out soon. All right. So then we have you see the connections. The for the weak bosons within that spin of one, we have the WC boson, which has different masses that I discussed with Christopher last week. and they form like the candle in a cave type of thing. Because W and Z and W has specific E over M versus the spin, characterizations. So, uh, okay. So they have chiral aspects, the vector aspects, things like that, that I talked about briefly in the beginning of this episode, of this text, of this session. And and then some ongoing things that's going on. Um, all right. So now we talked about briefly about the space, sense, and thing. So the coordinate axis, the five-dimensional coordinate, the sense, space, and the uh, time aspects. Okay. So that you can start the time aspect and the space, and we plot the sense. The idea is that when you do the tensor operation, sense has rank 2 tensor, which can be reduced to rank reduced to rank 1, and the space, the reduced and the expanded aspects. The space has rank 4, and Christopher has proved this. Probably it should be a 4-dimensional space. So again, there's a rank 4 that can be rank degradation. It's collapsed wave function type of thing, becomes 3. And the time again has 6 that I proved in my previous peer-reviewed papers and also presentation. The recent international conference called ICFAS have shown proof of that, rank 6, how in rank 6. And again, can really get it to rank 1, which is a vector. Okay. So then we can write in the normal notation, the vector notations, vector space, vector algebra notations of time, sense, and the space becomes the, if we put there t to the power m and gamma to the power 0, o should be o, okay? It's not 0, it's o. So let me put it like that so it becomes clear that it's not really a 0, but describe the rank of the matrix. And then you have the space x to the power n, and that can be reduced to it's r, this total to the and then you can add these exponents. And in the expanded thing, we see that that becomes 12 in contracted or shrunk space. I call the shrunk dimensions or reduced dimensions becomes 5. So that's how you get a Klein Gordon, the 5-dimensional space aspects, okay, of the sense, time, and space. But actually, the actual rank, which is probably dark matter. I mean, it doesn't exist because we believe that the future is a wave function that is waiting to be collapsed. So there are many words aspect that comes into picture. The future, that's why you cannot see the future per se. There are many possibilities, but based on the direction that Christopher talked about quasi-crystals, they define a path, and that path, then this wave function will collapse and it creates a real event path through which we go, and that becomes the future. So present continuously the how the present becomes future. So actually, the future is unpredictable in that sense. There's uncertainty, but then when it collapses, then it becomes real, and we move on, right? So we can actually see that it's not a continuous thing. It's a discontinuous process. That's what I'm trying to um, emphasize here, and that's becoming clearer with loop kind of gravity, things like that. The granular aspect of space-time coming into picture. So yeah. So essentially, I think I have covered, and then excuse me for some of the mistakes I did earlier, and any clarification to that effect, please bring it up, and I appreciate that. That will help to ensure that we are getting a correct picture. So that's the aspect as we discuss more and more. there are things that crop up, mistakes, of course, even in publication, and then we have to make corrections to that effect. But our discussions will bring out that, and then we can clarify that whenever that is necessary. So I appreciate that. It was a great pleasure uh, for letting me present this today, because my associates are not there today, but this is viewable because these are live broadcasts and it's recorded in our channels. And let me briefly bring some of the channels here so that is those who are wondering where these channels are. I think I can show. I can show where these channels come from. So this is the Technet Earth Global. Uh, you have see the YouTube Technet Earth Global. This is the link. This is the internet link. That's the website. You can get this popular. So today's one come. For example, I'll show you if this is showing up. I can show that here. I, all right. So history of physics, for example, this is the end of that. So the beginning, if you play that, so these are different aspects of today's. So you can see that I'm just demonstrating that how you can access these. So we have okay. So already the people are watching. So that's one aspect. And then so that's coming up. Then the leptogenesis, that's the previous one where I discuss all this with Christopher. Christopher has presented this, and then his presentations, and then in discussions that I talked about uh, some of the things that ongoing. That today I showed with some corrections, uh, some of the aspects. So these I showed you, and then I made the corrections for some of them, especially silly mistake like 100 gram equal to 0.01 kilogram, but it should be zero point 0.1 kilogram. So I just want you to note that you may have seen that. So you can bring it up if you make mistake in that. But also I showed how the time direction is determined by the gravity. Direction of the gravity is center of symmetry. So the gravity will not allow the time to go backwards. Okay. So we have arrow of time, which we think is based on the entropy. And similar previous ones you can see here, many. And you can also access the ones previous to that. And also I have given links to that. I'm going to show here per se, but you can go back. Um, so we have we have many views and the popular views, and people are, uh, like what vacuum research that Emmanuel has shown, the oldest aspects. Uh, okay, so the popular, so these are stream ad, but there are things that I think this is the older ones. Yeah, the earlier ones talked about the gauge discontinuity, and then we have also later on where John is presenting scalar theory. So we have many associates presenting at different times. So you can see that also. So those are and then the physics episode. So there are different ways we can access these videos, and the live broadcast is where we are doing it now with StreamYard. Thanks. we thank them for letting us do that, and then we get YouTube videos based on that. So essentially, that's what I want to bring out, and I think I know that is the main aspect. So. So thank you very much. I was able to then give a snapshot of what's going on to all people concerned, and we hope to expand this. Right now, it's within the group. We have the group of scientists. We are doing that, but we want to expand it. And one of the ways I think is having the documentary movie based on once we finish all the episodes. Hopefully by sometime before summer of next year, we'll start the documentary movie. Some initial drafts are there, but we have to work on that. The movies are always very expensive. But hopefully, by next year, towards summer or end of next year, we hope to have the first documentary as movie uh, aspect that covers all these aspects as well as some interesting aspects of physics related, phenomena. Maybe even Star Trek or Star Wars type thing that connects from the old theory that people were motivated and there may be an alien connection, we don't know. But that's something that exotic physics considers. So these are the interesting aspects, and there are a lot more coming up, more projects to the future we want to put together and hopefully have a world conference in different parts of the world Earth, as well as have probably a physical location, even we are talking about, and probably get together once a year at least in specific places in different continents. Maybe starting with Europe, we don't know, but later on, even North Pole, things like that. So that's the interesting way. And we established a world university, we can have courses, mostly graduate level courses that helps to get PhDs and things like that. And then understand applied physics, which we want to emphasize that to develop, with the quantum computing and artificial intelligence, coding, things like that. Physics coding may be the most important thing that's upcoming because many of the complex math can be put into algorithms. Then we develop the program to simulate them, and so theoretically we can prove them, and then come up with parameters that we can reasonably do even mesoscopic level, even tabletop type of experiments that can prove a lot of theories and makes the high cost experimental physics uh, amenable to normal aspect because eventually we have to prove with our own senses, right? Our eyes and ears and everything. It has to make sense to that what we see to what the physics is proposed. So this is the understanding of the natural physics that follows, and then we go through these crises or paradigms one after another to really understand that and see the inner aspects of the workings of the universe. So thank you very much. So, all your comments, feedback will be very useful. We hope to continue next week because some of our associates hopefully will hope, be able to come and able to attend, know, attend this test session next week to have group discussion and debates or whatever is ongoing and further presentations. And the next episode 8 is sometime towards the end of the third week or uh, of November, proposed to be. And there will be other presentations, discussions, interesting topics, and then current events uh, in the physical field, including Nobel Prize was awarded recently. But that was for mostly supporting artificial intelligence. So there's a lot of artificial intelligence. I use myself for research aspects, but you have to be very wary how the references gives and things like that. You have to really go through tooth and comb type of thing. So you have to expertise to really analyze them, but they are useful tool in research, to pull up things and then uh, even come up with the drafts, things like that, and then we had to do the further editing and detailed analysis. Going through them and sort out things to really make it meaningful to everybody. And we hope to have the publication, like discussing with Christopher, the 1,000 volume type of thing, which encompasses simple aspects. So, like encyclopedia of physics, so to say. Uh, Eventually, we hope to develop that and probably put everything together in terms of videos and movies, uh, many of them, so that it is understandable, also interactive discussions which will clear uh, the thought experiments, which are the basis, the underlying basis for much of the physics. Is the thought experiment that people started and eventually try to prove the experimental physics. So these efforts will keep going until we are in a good situation that we can understand reasonably well what we see or what we hear is what it is. And the kind of correlation between them. But there are surprising aspects because the future holds the key to the proof of the past and the present, right? That's the ongoing aspect that is exciting as well in terms of science, engineering, science, technology, engineering, and math. So we develop new products, new things that makes our life easier, and also a deeper understanding. And hopefully, robots and drones and the artificial intelligence eventually will be our main guide, eyes and ears, and helpful associates that will make our life, meaningful and continue easier to navigate. So we hope to do all that and excited developing aspects that's ongoing now. Thank you very much. Talk to you next week. Uh, so uh, I just want to brief that next week we'll have the same thing and the links will be available. And also this video that I briefly sampled are available anytime for a larger audience. And we hope to continue that next week and continue our quest for generalization. We are come up to quantum gravity, and we are touching upon the loop quantum gravity as well as the M theory, the brain theory, and brain theory. So we are very close to what's going on in this decade, right? But we have to advance very, very carefully, what I call algorithmic way of advancing to the next level of the physics, so that we don't miss that many other concepts. We can use that. The classical fields are very important because the concepts are important. For their modification, you need the actual in the quantification of them, and that's the key thing in all of the physics that's ongoing. So stay tuned, and then we will have more exciting things coming on. And I think we are in a position that we are able to quantify in terms of the coding aspects, and there are some successes. Simplification is the most key thing, right? The Occam's razor of things. Uh, as we go on, like Einstein did all that, finally he said E equal to mc squared, which was proved by other people in some ways. But that kind of a simplification is important, the energy mass equivalence and simple aspect of general relativity. And the quantum mechanics also is trying to do that with the Moneyvel's interpretation, but a lot more we have to go on, to really understand our complete aspects of the physics. So, we don't stop, at one level and then leave it confused, but we want to resolve this confusion, and that's what the history of physics is trying to do, a simpler version, so that everybody can see through that, and then see the where the confusion occurs, and then correct the confusion, the crisis that, of course, we go through. The philosophers, Krag and Popper and other, Nancy Cartwright, everybody is pointed out as we develop the theory, it goes through a certain crisis, and we are in that crisis aspect that we have to move away from to a better understanding of how the all the world works together, and we have to work together to ensure that we are getting the complete picture.